Welcome everybody that joined this talk today on World Environmental Day. I'm Paul Lourens. I present the Central branch of the Groundwater Division. I'm also at the University of the Free State Institute for Groundwater Studies, for those of you that do not know me. So we celebrate World Environmental Day today. So this year's theme is around land restoration, desertification and drought resilience under the slogan our land, our future. We are #Generation Restoration. So this is where we spotlight drought resilience with a special focus on managed aquifer recharge. And that's why we thought we can get Kes Murray in to give us a nice talk. For those of you that do not know Kes, Kes is a Senior Hydrogeologist at VGA in Australia, with expertise in Managed Aquifer Recharge. He holds a BSc Earth Science Honours in Environmental Geochemistry and MSc in Hydrogeology. With experience in testing, piloting, designing and managing MAR sites in South Africa, Botswana and Australia for potable water storage and mine water management. Kes also specializes in planning and analyzing borehole injection tests to determine suitable borehole and wellfield operational rates to assess aquifer responses to injection and to inform network designs. So Kes, welcome. If you're ready, I think we can start.
Thanks, Paul. Thanks for the introduction. I need to remind myself to make a shorter version for next time. That sounded a little pompous, but I'll give it my best shot. Thanks everyone for joining today. I've put this presentation together. Sort of managed aquifer recharge is something that I work in quite a bit, and I've put this presentation together to try bring more of a drought resilience / environmental focus to the topics that I normally discuss in this regard. As it is a free webinar and taking the time to put this together, the cost of that is that you have to start off by listening to me talk about the company that I'm at for a little bit, so that they get some marketing out of it. So I'll take you through a couple of those slides and then we can get stuck into some of the details. So the company that I work at is Wallbridge Gilbert Aztec, WGA, in Australia and New Zealand. We've got quite a few different offices, sort of north of 600 employees at this stage across those offices. And we are quite proud of a couple of awards that we won recently in the engineering and consulting space. You can see some of the details of them over there. There's nice big dollar value numbers on them. But we are very proud of them. That one sort of bottom left, best built and natural environment consulting firm, $100 to $200 million for 2024. These are client choice awards, so we're always very proud of them because it reflects the opinions of our clients and not just our peers. So yeah, lovely company to work for. We're a mostly engineering consultancy working across a variety of different sectors. So although I'm a hydrogeologist and work on water projects, most of my colleagues work on either coastal, marine, or civil, or geotech, or data analytics, or blowing things up and building new things and all sorts of interesting stuff like that. There's obviously, of course, overlap between these different sectors, which makes inter-office discussions very good fun. But that's what the company does as our core capabilities. And so just to say, when I say we've got 650 plus employees, we're not all doing managed aquifer recharge and hydrogeology, but some very interesting interdisciplinary discussions to be had. These are a couple of pictures pulled from different sites that we've worked at, and specifically in the sort of earth sciences and hydrogeology space. We really try and stay at the forefront of the industry and tackle water challenges with sort of unique bespoke solutions, looking to target individual problems that creep up within water management projects, which leads quite nicely into managed aquifer recharge. Across our water sector, we're not just dealing with sort of drinking water supplies, but we also look at stormwater as well, and wastewater management and all the rest of that. And then we have a couple of key areas with specialist expertise across the water group. So I've outlined a few of them that might be relevant for this talk for those interested. But key to that, I think, is probably the integrated wastewater or integrated water management, managed aquifer recharge, and then how that ends up feeding into water-sensitive urban design is a big buzzword topic around these days, which we get involved in. So I'll set the scene briefly. I think most people attending this might have seen this publication that came out at the beginning of this year. It ended up being put out through a variety of newspapers as well, but it was originally published in Nature at the beginning of the year. And it was essentially a global look at how groundwater resources are performing on the international scale. And as you can imagine, if I'm setting the scene for a drought resilience talk and a managed aquifer recharge talk, there's going to be a couple of highlights of declining groundwater trends. In this particular study, over 170,000 monitoring wells, about 1,700 aquifer systems across the world were measured. And yeah, there was a lot of greater than 0.5 meter per year groundwater level declines across many of those monitoring systems. Interestingly, towards the end of the little abstract section at the beginning over here, there's also a couple of reverse trends where declined groundwater levels have since been recovering. And those are attributed to either policy changes, specifically attributed to managed aquifer recharge, and cases where there's surface water diversions. And for those of you familiar with this, apologies, but I do find these images quite interesting. These are some of the monitoring well trends looking at how much change has occurred in the monitoring data. I believe it was over about an 8-year time period. I might be off by a year or two over there. But more importantly, they also looked at broader aquifer systems, which mostly reflected similar patterns. You can see a zoom in at the bottom for South and Southern Africa over there, zoomed in further under image G. And where they had data of the aquifer systems over there, they tend to be in the orange or the red, not in the blue or the green. So that's sort of the scene in terms of addressing drought resilience and setting managed aquifer recharge up as a tool to do so. I'm going to go through the presentation quite quickly. I'm not trying to get into too many of the difficult technical weeds details. What I'd really like to do is, once getting through this, if there's questions or discussions that anyone would like to have on some of the stuff, I'd really like to hear those and do my best to answer them, or admit that I don't know how to answer them. So we'll see where that goes. So just a couple of images on managed aquifer recharge to sort of set the suite of technologies that we have. There's many high-end professionals that deal in very niche aspects of managed aquifer recharge. So some people just deal with injection, some people just deal with aquifer storage and recovery, or aquifer storage transfer and recovery. Some people are just on the infiltration trenches and pond side of things, but there are a whole suite of methodologies available. Some of the interesting ones are stuff like at the bottom left, the soil aquifer treatment. That's an aerial shot of one of these sites in Australia where they're doing soil aquifer treatment up in the Northern Territories. But there's a variety of different methods by which we can get available water sources back into aquifers, or for the first time into aquifers, as quickly as possible. The top left photo over there is some of the larger infiltration basins in the world. This is out in California, and I had the pleasure of visiting a couple of them at the last ISMAR conference, which occurs every 3 years. And yeah, I'll have a slide on that at the end as well. Top right over there is a local favorite of mine. It's the groundwater replenishment scheme in Perth. This is a advanced wastewater treatment facility, which re-injects, I think, in the order of over 100 liters per second back into the deeper aquifer, where it's replenishing groundwater abstraction that's being used in the area, and helping with the water balance. Locally in Perth, I'll touch on that for a second. The groundwater is, especially the shallower groundwater aquifer, is linked to groundwater dependent ecosystems. So although we're in an interesting situation where, although if you look at the volume in storage and you look at what's available to use, there's massive amounts of water available in storage, the fact that it's all linked to environments that are dependent on those levels being very tightly held at those elevations and at those pressures means that a lot of the time, although the water is there for use in storage, it can't actually be used unless we start treating other water to recharge and replenish the supplies that we've got. So this is a big scheme in Perth that's been investigated over the last decade for tests and trials and bringing it up into operations, and ran for about a year or two, and now they've increased their operations again. I think the endpoint target is to have the capacity to do about 28 gigaliters a year, if I have those numbers correct. So yeah, very interesting to see that applied close to where I live now. I always touch base on this when I'm talking about Managed Aquifer Recharge, because I try to encourage as many people who are interested in Managed Aquifer Recharge as possible to use it. This is IGRAC, the International Groundwater Resources Assessment Center. They have an online MAR portal, which keeps a record of international MAR sites. The thing that's very nice about this website and this platform is that they've filtered a lot of the information according to several different categories. So what the objective of the MAR scheme might be over here, just outlined, if you look for the color coding of ecological benefit or something that might be of environmental benefit, not just specifically storage or water quality or reuse for town supplies, but environmental specific benefit, you can see that there's not that many schemes relative to, for instance, in Europe, all the water quality management schemes that are set up over there. So it's quite interesting to use this platform and this tool when considering new potential schemes, and to go and look at, what influent source water type were they using in a specific area, and filter according to that. For if you are considering a new scheme or the design of a new scheme or the feasibility of a new scheme, you can go look at other schemes across the world that have either used a similar water type inflow. Maybe it's stormwater harvesting, maybe it's treated wastewater, maybe it's river flow, maybe it's transfer from one aquifer to another. And you can go and find the references to those projects internationally to go and look at, maybe the method that they used is something that's specific that you're wanting to try and use at your site. And it's quite a good background reference tool to go and get in contact with the people that have worked on these schemes and published on these schemes, but also to see, what went right, what went wrong, what type of volumes were they able to do for a injection bore or injection borehole versus a massive infiltration basin. This is a site that we worked on as WGA in Australia. This is a Managed Aquifer Recharge site specifically for environmental benefits, and it was the Catarapco floodplain, where essentially what happens over here and what the environmental benefit that we're trying to achieve is there's a large floodplain around the River Murray, and which will flood every couple of years at whatever frequency, and the residue of that leaves behind salt deposits along the floodplain. And so the vegetation that's over there is adapted to some brackish to saline water quality, but in some cases there can be large areas of the vegetation that dies off because of these residual salt deposits from the floods. And so the idea with this was to, even outside of the generally, if you've got enough rainfall, you'll have some freshwater supplies helping the system. But as rainfall declines and diminishes, the idea was to collect fresher or lower salinity water out of the creek or the river and transport it back inland, a little buffer way in. This was a trial that was set up, so this is not the full application of the scheme, but transport it inland and re-inject it into the aquifer to facilitate a freshwater lens within the saline aquifer that can, and this is not for human consumption, this is just about enabling vegetation to grow reliably as the sort of natural freshwater inflows to that area start diminishing. So this the type of fun stuff that you can do during a trial, to go and do geophysics and see exactly if you can find the bubble of water that you've put in the ground or not, and if not, why. This is another site, totally different example. This is actually where we were looking at using Managed Aquifer Recharge to offset dewatering of a temporary works construction site. So this site is in Australia, and the purpose of it, this is a 3D model of all the infrastructure around the area. The purpose of this site was that we were constructing a tunnel, so it needs to bore a tunnel underground, and the earthworks underground are below saturation level, so you have to put cut-off walls in, and you have to have dewatering to make sure that the site stays dry while you work at those depths. The problem is that there is, as you can see on the right-hand image, a lot of nearby infrastructure, and if we get too much drawdown from the dewatering and cutting off the water, that can cause settlement issues. So when you're dealing with massive, large diameter sewer pipelines nearby a residential area, settlement is something that the geotechnical engineers will tell you is a bad thing, to use the technical term. On the western side, there's also groundwater dependent ecosystems, which are environmentally protected. So essentially, we set up a reinjection scheme around the site to hydraulically buffer the drawdown outside of the site while still enabling dewatering on the site to do the temporary works over there. So this is a little CCTV snapshot into the site. You know, you can see the little orange ants down at the bottom of the site. Those are the people working in the site. This is the size and scale of what we're working on over here, making a huge highway tunnel going underneath the residential area. And like I said, so that site needs to be dewatered to work in the way that they're working over there. But at the same time, you can not impact the surrounding aquifer and environment as much as you otherwise might. This is more onto the sort of drought and sustainability side of things. This is a reinjection site where we've got a groundwater dependent ecosystem quite a bit further away from the pit that needs to be dewatered over there. And so we've got injections set up between them. And this is, in some sense, a bit of a schematic or conceptual graph. But if you follow the red trend over there, that gives you an idea of the natural declining groundwater level in the area close to where dewatering is required. There is already a drought curve over there. And the issue is if this, if that continues and gets exasperated by the dewatering activities, although you might have temporary works or longer than temporary works time frame dewatering, the rebound time for that aquifer to come back up is going to be sort of, you know, we work on logarithmic timescales over here. So you might do dewatering for 10 to 20 years, or you might do it for 2 to 5 months. But that final 5%, that final 2% of recovery to get those aquifer levels back up can take a lot longer than it took to dewater them in the first place. Now, in particular, if we're dealing in a drought environment or a low recharge environment, you might never reach that again. So there's a big emphasis, this is an Australian case study, there's a big emphasis over here to make sure that dewatering volumes and excess water volumes near dewatering sites are not lost to evaporation for temporary timeframes, but are rather reinjected back into aquifers to replace as much of that water balance as possible, but also to assist with that rebound time. You can think of a cone of depression that you would create around a dewatered site or a high, even just a normal high abstraction site. If you then switch that off, it's going to take a certain amount of time to rebound. If you have an injection cone superimposed on top of that in one area or in multiple areas, you can speed up that recovery time quite a bit. But you do have to be careful about planning how you do that. Just to take a short detour down this, there was actually a publication last year on implementing Managed Aquifer Recharge for dewatering sites. I won't spend much time on this, but it is a worthwhile publication going to take a look at. Not least just to see the scale that some of these people do things at when you go into the mining industry specifically. So this, again, I won't spend much time on it. Frequently, the types of volumes that we used to talking about with boreholes and groundwater supply, we're talking some of the rural areas, we're talking 1 to 3 liters a second, half a liter per second, 0.2 liters per second. Sometimes, if we're lucky, we're talking 10 liters a second. And frequently, when we're talking 10 liters a second, 2 years later, we're actually talking 2 liters a second. These guys are re-injecting at 185 liters per second when they started operations. In 2023, it's about 4 times that. Oh, it was about 4 times that last year. I'll skip through some of this. This is another specific site. These guys are probably the leaders in terms of total volume. They have abstraction out of a saline aquifer, so they, for environmental purposes, can't push that excess water down a creek. They're now in the order, as of 2024, of 5,500 liters per second that they're re-injecting. So this is not to say, bigger is always better and who's the best type of thing. This is to say this is a proven technology and methodology that can be applied across a variety of different settings. So when we're talking about secure water supplies, when we're talking about drought resilience, when we're talking about environmental protection, it's not to say that, oh, we're not entirely sure where the water is going to go. We're not entirely sure how to apply these methodologies. No, these methodologies have been applied for decades and they work effectively. We know how to do this as an industry. Quick look, this is actually from a couple of years ago when I did my honors back in South Africa. One of the mines over there, we did a 10-month trial to pilot injection, created a little mound under drainage channel over there. Big thing to understand when you start getting into injection-based managed aquifer recharge schemes is what is the aquifer doing and what are your injection holes doing. You see the same thing on the dewatering or the groundwater supply side of things. The sustainability of the point at which you abstract water and the rate at which you can inject water is a separate thing from the sustainability of the aquifer system or the rate at which you can get water into the aquifer system. It's a frequent mistake or confusion with sort of people that are inexperienced in bigger picture thinking on groundwater aquifer systems is to mistake the performance of an individual borehole, whether it's monitoring or production, with the performance of the actual aquifer. It's similarly a mistake that happens where you look at the performance of an aquifer and try to infer the performance of a specific production borehole. Especially when you start dealing with complex fracture networks and dikes creating compartmentalization within the aquifer. But that's a little bit onto the technical details. One of the major things we do need to overcome with managed aquifer recharge via injection and infiltration is to make sure that we don't clog our recharge sites. So these are this is what clogging looks like if you've got iron and suspended solids and muck and clay and stuff in the sites. The same thing happens in an infiltration basin, and particularly with regards to an infiltration basin, the risk that you run is when you go in to clean the stuff out, the equipment that you go in with, usually quite heavy machinery, ends up compacting the bottom of the infiltration basin floor. So you have to have quite careful designs prior to the clogging occurring to allow that cleaning crew to come in and the cleaning equipment to come in, scrape away what's there, move it out without overly compacting the bottom of your infiltration site, because as it becomes more compacted, your effective infiltration rates going downwards will decrease. The infiltration rates outwards through the sides of the pits will still be fairly good. So this is one of my favorite graphs. It applies to all things hydrogeology and also to managed aquifer recharge. It is the Dunning-Kruger effect, and it's a graph of confidence versus competence. And usually the reason I put this graph up is partially a warning to myself and partially a warning to other young water professionals. The term young should give you a pretty good indication of where you might be sitting on this curve. And it's important to remember not to be too confident kind of coming out of university studies, because there's a little bit of a learning curve just ahead of that. So hopefully that drop down to the value of despair isn't too painful an experience, and then we can start actually becoming a lot more competent. If we don't get that right on a re-injection site, we end up spilling water out on surface. Usually what we're trying to do on these projects is get a guru involved. So the local guru that I turn to is Russell Martin. He's our water sector group lead at WGA, and he's got a couple of decades worth of managed aquifer recharge experience. He's also written, and this can be found through the IAH website, there is a managed aquifer recharge working group, and within that there is a clogging monograph that Russell's compiled with a bunch of published texts and case studies on how managed aquifer recharge systems clog, how to predict them clogging or having the potential to clog, and then how to manage them as well. So go check that out if you're interested. A little whip through of a couple of things to look at prior to the design of a MAR scheme. It's well known that recharge wells will require some sort of a backflush frequency to manage the expected level of clogging that occurs in them. So occasionally you can get away without any backflush, and usually that is dependent on having good source water quality naturally, or good source water quality treatment. But by and large, one of the things that needs to be accounted for in a reinjection scheme is an understanding of how frequently you're going to need to backflush. If you don't backflush, the clogging that occurs in the screens essentially means that for the same rates that you inject water in, the required pressure within the bore, which translates to water level under gravity systems, starts rising for the same rate of injection. And if you don't have a well-constructed headworks like the picture we saw earlier, that will spill out on surface. If you do have well-constructed headworks, it means you'll start pressurizing those headworks, which you can design for. But at some point, you end up exceeding safe operating pressures. And what that means, which we've seen before, is you pressurize the bore and its construction to the point where the pressure will lift the injection bore, start lifting it out of the ground. Usually before, don't worry, it's not going to get too far out of the ground. The fracturing as it comes out of the ground allows the water to escape and you flood the site. So something to be careful for, or something to be considerate of, when the reason we get so concerned with clogging is not just about getting enough water into the aquifer, it's also about managing the infrastructure that we use to get that water into the aquifer. So there's a couple of downhole shots of what some of these things look like. Some of those photos are from Australia, some of them are from South Africa. But generally what we want to do is understand what the potential concerns are chemically, as well as for physical clogging, suspended solids in the water, and then also have an understanding of how we expect our aquifer to perform during injection, as well as what we expect to start happening when there is clogging, so that we can have an early warning detection for that. As a general guide to taking on a new managed aquifer recharge project, there's usually a hydrogeology component at the beginning. This is why there tends to be more pre-feasibility studies and feasibility studies than there are MAR schemes, certainly in South Africa, as far as I'm aware, but in the rest of the world as well. But this is quite an important component to get right, because the engineering component of designing a MAR scheme is equally as important, but it is dependent on having the hydrogeological understanding correct. And what I'd say is probably most important in that is having a good understanding of not just what the data and information that you have tells you is possible, but the amount of variability that can be expected to occur within that. So as an example, if you're looking at a aquifer storage and recovery site, so you might want to be banking water for a couple of years in case a drought hits in 5 years' time. It's important to know, okay, well, how much storage do we expect we can get into the aquifer? What rate do we think we can get it in? But if we're wrong, how wrong are we? And having an idea of how wrong we are is a really important detail when we feed this hydrogeological information onto the engineers, because that has influence on things like the size of pipes and pumps and valves and filters and operating procedures and all the rest of it. And it's a tricky thing to bridge this communication gap. A lot of the engineering details are very, very precise and very, very high resolution decision making, whereas a lot of the hydrogeology details can be a bit more broad. And so usually we start getting asked difficult questions like, what would the best case scenario be and what would the worst case scenario be? And then what do you want me to design for? And that really requires a lot more discussion than just an answer or an email. So just a word of caution on that end of things. But once the hydrogeology is sorted out and If there's no engineers on, then we start arguing with the engineers about what we're actually going to do. If there are engineers online, apologies for that. And so the hydrogeology feeds into the engineering design. This goes through sort of several phases of design, and there's a whole raft of complexity there before it goes into the actual construction and then commissioning and operator training. These three sections, the hydrogeology to the engineering and then to the operations, each of those red arrows that tie them over there, that is where there's the most potential for communication gaps and for information to not correctly flow through to the operations of a system. So one of the key things one key concept that highlights this very easily is there's the idea of talking in units, so liters per second, cubes per day, megaliters per day, gigaliters per year, all of those interchanges. That's just converting between the units isn't the real issue. The real issue is when it comes to a peak capacity of the different components of the system. So we might require infrastructure that can allow us to inject, as an example, up to 10 liters per second. But we know that most of the time we're going to be injecting 2 to 5 liters per second. We also might know that the total volume is not going to be the equivalent of 5 liters per second 24/7, but more like half a liter per second 24/7, with huge changes in flow rate depending on what our source water supply looks like. Now, that type of information needs to feed into hydrogeologically. Can we accept those peak flow rates, or do we need a cutoff? But then feeding back into the engineering, what do we need to do in terms of aquifer level and pressure responses in the injection bores when we have that type of variability? So for instance, we might get flows of 5 liters per second for 12 hours a day, and every now and then it jumps up to 20 liters per second, but it's only for 15 minutes. We might need storage buffer to sort that situation out, but we might also just say, look, we can't accept that water. On the other hand, we might have bores or balls that can accept those high volumes, and then we can just send that all down. But we might decide that the actual flow velocities inside those injection boreholes aren't suitable because we're going to entrap air bubbles that's in the water. So we need some settling period, even though the borehole can accept the flow rate. So those type of nuances between injection rates, variability, daily volume variability, and then annual volume variability, that goes onto the policy and the permitting and licensing side of things. But those nuances are the types of things that end up getting dropped between the hydrogeology and the engineering side of things. And then similarly, when it comes to the programming and the logic control of these systems, which end up being mostly remote and automated, those type of decisions need to follow through as well. When do things need to backflush? How do we make sure that we're not backflushing too frequently? All of those type of decisions. So just a word of caution over there on those connections. I'll skip through this. I think most people have seen a pumping test. An injection test looks like a pumping test upside down, except you generally end up getting different parameters. Won't go into the technical details of that, but it's important to do an injection test. And if you're not going to do an injection test, it's very important to be conservative on your estimation. Some of this stuff tells us about how aquifers respond to pressure changes, sort of analytical models of either when you do a pumping test or an injection test. And it's important to get a grasp on the stuff and to understand it, especially when you start dealing in a fractured aquifer, which a lot of Southern African aquifers are. When you start dealing in a fractured aquifer, I think that some of the things over there, those plot H, N less than 2 and I greater than 2, these relate to fracture network geometry. The Barker solution has a bit of discussion on that. Those type of things, there's some quite good South African literature on the expected long-term performance of groundwater levels under pumping conditions in fracture networks, and they tend to go to a fracture network geometry of N less than 2, frequently closer to 1 or 1.5. That is quite important implications on long-term extrapolations of test pumping data, and the same for injection data. So it's important to have some sort of a conceptual understanding to marry to your test analysis in designing what rates you're going to inject under. For all of these graphs, you can picture if they were the other way around, these would be rising pressures in your bores. And if you've designed everything correctly, that means that your headworks are sealed and everything operates smoothly. And if you haven't, it means either something's going to pop out of the top or you're going to have water spilling out on surface. There's a couple of details in here that can go through some of that, sort of operational philosophies, management plans. It's important to understand all of those things. These are a couple of the items at the top over here that go into a safe operating pressure. These are essentially the things that can go wrong if you've incorrectly calculated the operating pressure. Not sure how relevant that is to this discussion, but there are a couple of dot points over there to consider. Essentially, the thought process is if I keep increasing the pressure over time, what's the first thing that's going to fail, and what can be engineered out, and what is an actual limitation on the area. But you end up with some fairly complicated headworks. You know, these are looking at aquifer storage and recovery sites, which means that the water that's injected into the aquifer gets re-abstracted out of the same hole. But you frequently have these type of headworks, even if it's just a dedicated injection hole, because you need a downhole pump to be able to backflush your injection bores. And so a couple of the key considerations there is in selecting how the length of screen that you have in that borehole, or casing, or where that's cased. You're going to need as much in primary aquifers, you're going to need as much screen length as possible to manage your flow velocities, but you're also going to need them starting as deep as possible so that you have an available working head area for when you backflush the bores. So quite a detailed, nuanced borehole design goes into all of that. And that's mostly the end of my presentation. It's just sort of general awareness around managed aquifer recharge. That central image is a South African site where groundwater levels were recovered and water quality was reduced in salinity by doing a little more of an enhanced aquifer recharge than a managed aquifer recharge, but sort of effectively demonstrated the potential of what could be happening there. I'd like to take 1 or 2 minutes if I've got a bit of time, which I hope I do. Paul, will you shout at me if I haven't got time?
I will do that.
Okay, great. So I mentioned it earlier, the ISMAR, the International Symposium of Managed Aquifer Recharge. It occurs every 3 or 4 years. It's in a different country each time. I was lucky enough to go to the last 2 of them, which was in California last time in the States, and Madrid in Spain the time before that. The next one is going to be in Stellenbosch in South Africa. And I would really encourage anyone interested in this field, whether it's from a hydrogeology perspective, an engineering perspective, or water management perspective, hydrochemistry perspective, to really consider, hopefully presenting, submitting a poster, something like that, but even just attending. The thing that I've found going to these conferences is there is a core group of international professionals in this field which go around to each of these conferences to all catch up with each other every couple of years. And those people essentially are, trying to think of the correct way to describe them. I've been to conferences before where you're almost worried about how much information you share. These ISMAR conferences are more like, if you could picture a very excited 8-year-old child that's been working on a project at home for a long time and can't wait to share it with their classmates. That's the feeling of these type of conferences. So if you are interested in getting involved in managed aquifer recharge and speaking to a lot of the people that you'll have seen referenced in papers, if you're doing literature reviews on this stuff, or even just getting to understand how some of these professionals think about aquifers from the perspective of recharging them with infiltration basins or injection bores, or any of the other methodologies, I'd really encourage you to come along. There's some really smart minds in the room, and they are very, very eager to share the information that they know, and especially if you've got projects and questions to ask them, whether they are theoretical or practical for implementation. They're very, very keen to discuss data, give you some words of wisdom, and share whatever they can to help. So there's a website up. I think we're open for abstracts. There's an open call for workshops. There's themes and sub-themes and all sorts of information up on the website. So I'd really encourage everyone to check that out and come along and attend. It will be next year, April, May 2025 in Stellenbosch, and I'm really, really looking forward to it. And so I hope to see as many of you that are attending there as possible. But if not just for seeing me, then come along to learn from really the cream of the crop when it comes to managed aquifer recharge across the international scale. Yeah, and then my closing slide is more about how much fun I have at WGA than anything else. The quote at the top right over there is probably the take-home message from that. So here's a snapshot of a couple of the managed aquifer recharge projects that we've worked on. And with that, I'll close. Thank you very much.
Thank you, Kes. Great presentation as always. Before I open the floor for questions, just a quick announcement about the poll after we finish. There will be a poll just for the CPD purposes. You can just complete that before you switch off. Then you can pop up your question then in the chat box. I will read it to Kes. And then maybe I will quickly start off with a question, Kes, just to get the chat on the go. Can you maybe share successful examples of AMR projects that have improved drought resilience or maybe in some lessons you've learned from these projects?
Yep, absolutely. Yeah, I think I ran a little bit over time what I was planning to, but I was hoping to have some chats and discussions about this type of stuff. I think sort of thinking about drought resilience specific projects, I mean, probably the best example that's closest to home for South Africa is the Windhoek example. And hold on, I've completely lost my screen here. There we go. The Windhoek example is, in Namibia, and I don't have a huge amount of information to share on that, but sort of the overview from it was essentially Windhoek was able to preempt the onset of a drought by banking water. So round about the same time that Cape Town went through the sort of day zero crisis around 2016, 2017, 2018, Windhoek went through something similar, and they'd been banking water, I think, for about a decade at that stage. And so the town prior to that was running on about 6% of its water supplies was from groundwater. And with the onset of the drought, they were essentially otherwise screwed and managed to ramp up their groundwater percentage of the supply to about 45%. Very, very quickly over a couple of months, because they'd been banking for a decade before that. So that's probably one of the best ones closest to home. I think the takeaway from that one is pretty clear. It's you need to start early. And that's really a key thing to remember is managed aquifer recharge is not a drought management tool once you're in a drought. In fact, most drought resilience methodologies and ideas have nothing to do with what you do when you're in a drought. There's things you can do, great. Cape Town learned a lot from doing them, and I'm sure the rest of South Africa has learned a lot about it as well. But most of the stuff you can do is before the drought. And so having a managed aquifer recharge scheme in place, I think that one is mostly sourced from treated wastewater, gives you that resilience to get through the drought when it does arrive. I believe at full capacity, they've got something like 2 years, it might even be 3 years water supply purely from banking up water from when they started that scheme. So that's operational, running, awesome success story that's close to home. A couple of a couple of examples outside of that is sort of one of the ones that we've worked on in Australia recently, and there's another one in Spain that comes to mind that I learned about from one of these Managed Aquifer Recharge conferences. That in Australia they take the water security and safety far more seriously than what I was previously used to, I think would be a good way to say it. So one of the sites that we're working on, they're essentially predicting that they might have a water balance issue and a water supply issue in about 2040, maybe 2045. And so essentially all the residential developments in that town area that are being developed from now going forwards, all of them have rain or roof water harvesting runoff going to a centralized scheme for reinjection into the aquifer, just to get that banking starting. You know, we're in 2024 now. Realistically, it'll probably start in the next couple of years, but they'll again get probably over a decade's worth of banking in prior to actually having the need for that water. So it's that type of forward thinking that really is required to do this. Another one, a friend of mine that I've met at ISMAR, I can't for the life of me remember his full name, but Jose from Spain is how I remember him. Recently did his PhD on a sort of climate change adaptation with Managed Aquifer Recharge. And so specifically on the drought resilience side, the case study that he looked at was an aquifer sort of northwest of Madrid in Spain, and looked at essentially the reduction in cost from having Managed Aquifer Recharge in that aquifer, as well as that was one of the sites in the world where they actually had recovering groundwater levels due to the Managed Aquifer Recharge scheme that they had over there. So there's a lot of them around. I think probably if someone's looking for a specific reference, I would point them to, there's a publication from a couple of years ago called 60 Years of Managed Aquifer Recharge. I think the lead author is Peter Dillon, and there's probably about 20 authors behind his name. That would be the reference to go to for successful Managed Aquifer Recharge schemes.
Thanks, Kes. I don't see any questions from the floor. Maybe I can pop one again. What are the emerging trends and future directions in MAR and technology, if you are aware of any?
Yeah, there's a really interesting thing happening in California at the moment. I think they've actually got a presentation out on YouTube on this. If you go and search probably Orange County Water District and then FIRO, F-I-R-O, and Prado Dam, you'll probably find it. What they're doing over there is incredible. They've got a whole dam system set up in a catchment, and the excess dam water release goes down to their recharge basins, these infiltration basins, which are just ginormous. And what this development is essentially, they've been trialing it, I think, through 2023, and it's now fully implemented. The FIRO's goodness gracious, I'm blanking on what it stands for now. Forecast Informed Reservoir Operations. That's it. So they have their rainfall forecasting with a live link to their water release from the Prado Dam. And the reason for that is the dam has a point at which not the height of the dam wall, but it has a point at which it can't fill up further because it starts having environmental flooding impacts. So they have a spillway to let water out. But obviously, if you've got rainfall coming into the dam for a certain amount of time during the year, and then that slowly gets released out at the rate that the infiltration basins can accept, you want to manage the levels in your dam so you don't run out of water before the next year's rainfall event. So there's some conservative estimates in there, but you also don't want to get to the point where you've left too much in the dam, not sent enough to the basins, and then a big rainfall event comes and now you can't store any of that water in the aquifer. So their system, and I'd really encourage people to watch this. It's super interesting. They'll have forecasts of rainfall coming in, and they'll be releasing flows to the infiltration basins based on the probability and the density of rainfall coming in the next couple of days. So the forecast informed operational levels or reservoir operations. And the example that they gave was they had a massive hurricane come through, and they had sort of the live technology that's fluctuating their outlets, changing their levels as they were going through a flooding event, so that they could get as much water out into the infiltration basins beforehand, and then during the actual rainfall event itself, they were changing those levels live to get that out there. So I think that's sort of a very fancy technology application of innovations in managed aquifer recharge. I'm not sure how applicable that is to the rest of the world, where we don't have American budgets to play with, but that's certainly an exciting one. I think probably one that is not quite as fancy and doesn't get as much attention, but something that I was very interested in 2019 when I went to the Madrid ISMA, was the soil aquifer treatment managed aquifer recharge schemes. And there, some people were looking at essentially constructing large subsurface filter basins to assist with wasted or wastewater treatment. So some people were looking at, instead of using sand filters, using sort of volcanic tuff material, because it might absorb some of the chemical parameters more effectively. Those, I don't know how well they scale above the small scale stuff. It depends on available materials, but certainly a very interesting application of using managed aquifer recharge technologies, not to specifically recharge an aquifer, but to just do endpoint treatment from a wastewater plant. So no long storage times, no actual aquifer management, but the same technologies applied over essentially a very big subsurface filter.
Thanks, Kes. Just a comment from Dr. Roger Parsons. Just a great presentation, Kes. Thank you. I couldn't agree more with you more regarding being prepared for a drought. Taking action during a drought is too late. I think we all can agree to that. Then a question from Farners Free. Hi, Kes, you mentioned that there is a misconception regarding the pump test volume versus the recharge volume of the aquifer. Can you please explain?
So is this firstly, I should just say thank you very much, Roger. I still owe Roger a catch-up phone call sometime. So Farners, you're asking me to talk about the bit that I said I wasn't going to talk about because it was too complicated for this talk. I just want to check that that's the exact question that you're asking. So the issue here is, when the technical side of it is, when we look at the rate that water can be supplied sustainably or reliably from a borehole. That is dependent on the borehole characteristics as well as the aquifer that it's in. And one of the issues, and I think this is something that I think it was explained well and mathematically in some of the original FC method publications, and I don't know whether we have always done the best job as a groundwater community to pick up on some of those nuances. But one of the issues is that in fractured aquifer systems, a lot of the time the pumping test data does not have the derivative and second derivative towards the end of the concentrate test that will be totally reflective of long-term production levels. Sometimes it does, and sometimes it gives those predictions very accurately. The issue is where, and I believe this was talked about properly in those initial FC publications. The issue is where conceptually the pattern that we see during a pumping test response does not match the geological setting of an area. And if we have I'd like to say, if we have a disrespect of that contextual setting, disrespect's probably not the right word. If we don't account for the broader geological setting, we run into the issue of seeing a very low derivative response to drawdown, very flat slope to drawdown, and then not accounting for the fact that at some point, once we've overcome initial storage levels within compartments, we might not have seen those boundary conditions during a pumping test, but we will see them when we're talking about a 10 to 20 year production of a water resource. Now, where it gets complicated is I think the reverse tends to happen sometimes when we try and do the same exercise through numerical modeling, because there we're overemphasizing the context of the area and not sufficiently well understanding the individual performance of production boreholes. So I think it goes both ways. I think they both need to be accounted for. Where this gets tricky, so for instance, in Western Australia over here, there's a large mining area, which is kind of similar to some of the mining areas in South Africa, where we have dolomite aquifers, karst environments, and bandadine formations which get mined, and we've got dikes that go through the area, very similar to some of the Southern African settings. And frequently where we have these dike swarms going through, we have compartments within an aquifer. And the problem is when we set up numerical models, we might not have all of those dikes mapped out, but we might have some analytical data which gives us our basic aquifer parameters. So we extrapolate those generalized aquifer parameters over the geological mapped area without a good understanding of where these dikes are forming boundaries, where they are forming additional flow paths laterally through an aquifer. And then the numerical modeling side of that can easily overestimate storage within an area that can't be accessed by individual production bores. When we start injecting into that, what ends up happening is we fill up a compartment too fast, and then we have pressure issues. This is an interesting topic in mining context, because they're trying to not just re-inject water when it's available, but consistently manage excess mine water. So if we run into oversaturation issues prematurely, there's questions asked. So yeah, important to think small scale and big scale all the time. I hope that answers.
As far as I hope we answered your question, but I think you can contact Kes afterwards as well to have a discussion.
If not, Farnes, I'll see you at ISMA and we can discuss it there.
Okay, I think we've come to the end. Thank you everybody for joining, taking an hour out of your busy schedule. I know most of you are consultants and your schedules are quite hectic. Kes, again, thank you for your time all the way from Australia joining us. We appreciate it. And we're definitely looking forward to seeing you at ISMA.
Absolutely.
I definitely want to go this next year. Okay, guys, just remember about the poll. And thanks for joining. Kes, go well. And regards to all the people we know.
Good evening, everyone.
Thanks, everybody.